This is joint work with Professor Diego Gomes, Francisco Miller, Nuria Prauchik, and Robert Heath, and several students. And I'm going to try to give you a brief introduction about the problem, and I hope to be able to answer questions. So just to mention to you that we are located in North Brazil. We are a large university with the mission for the sustainable development of our region through science and technology. I wish I could basically be telling you about, let me see if I can manage to do this. I wish I could show you the wonderful forest that we have on our campus, but unfortunately I'm stuck in an apartment. So basically, I'll go ahead with the presentation and tell you that beam selection for 5G MIMO is important because we need to use large bandwidth to achieve high capacity. As this channel capacity equation shows you, basically what the 5G new radio is doing is using not only the sub-6 gigahertz bandwidths, but also large chunks of spectrum in these millimeter wave bands. So basically one problem that we have when we have millimeter waves is that the stronger attenuation makes the signal weaker. But then we can use multiple antennas in MIMO systems, and then we can provide beams and increase the reach and also minimize interference. So the discussion here is going to be focusing on millimeter wave. And if you look at what people can do when they go to millimeter wave, basically the antennas, they can be packaged, because if you look at the way the wavelength is related to the frequency, the larger the frequency, then you can pack the antennas. And also you can improve the radiation pattern. For example, here I'm showing for one antenna and then from two antennas. And basically, if you see for several of these antennas, you can provide what people call a beam. And this beam can be directional, but also can be like this one, for example. Because basically what people do most of the time is they impose for the antenna array, for example, a vector of angles, and then moving these numbers or changing the numbers, you can basically achieve, for example, these beams that I show here. And sometimes you want to point straight to a direction, for example, if you are in line of sight, but some other times you basically want to detect multipath components coming from several directions. So sometimes this kind of beam is better. But basically the idea here is that if you have millimeter wave, you can have more antennas packaged, and then you can have flexibility on choosing the beams. And if you look at how people are using that on 5G phones, basically I'm taking this Qualcomm antenna module as an example. You can see it's very small. They don't mention explicitly, but people say they can pack 64 antennas there and also support several frequency bands. And they basically are incorporated in these modern phones as modules. For example, you can see here 4, 1, 2, 3, 4. And in this other phone, you can see 3 of these small modules, 1, 2, and 3. And basically, when you're dealing with a smartphone, you have to control, for example, blocking from your hands, etc. But for this challenge, we are going to be dealing with vehicle to infrastructure, because it's more, let's say, predictable, the path that the car takes, for example, on a street. And based on that, we are going to be dealing with this beam selection problem. So this slide is a little packed, but let me try to show you that whenever you are doing, for example, the first connection, you have to select a pair of beams. Let's say the transmitter has multiple antennas and also the receiver. After these beams are chosen, then you can track and use less overhead. But basically, this is the architecture that's called analog architecture. And you have the beam forming on the transmitter and the combining on the receiver. And what people do is, as I mentioned to you, each of these phase shifters, they are specified, the numbers here, basically multiply the signal. And these numbers comes from a vector that's specified by a code book. you can think of, for example, a code book at the transmitter having empty vectors, we are going to call F, and at the receiver, you also have another code book, and then it has MR vectors, and we are going to call W. And basically what we do is, for this first selection of a pair of beans, you are going to search. And of course, you have to take into account the wireless channel age. And if you try a brute force approach, then you have to try all possible combinations. And this may be a large number if you go seeking the best pair one by one. Here I'm trying to provide you an example. If you are looking, for example, for cars, you have high mobility, but as I said, it's a predictable trajectory. One thing that we want is to increase the number of antennas. But then, as you can imagine, you have more beans, but this also implies on the fact that you have to try more pairs. And what we know is that machine learning can decrease these communication overheads by letting you choose a subset of candidates. And this, as you see here, as you increase the number of antennas, the beans get, let's say, more pointy, but then you have to deal with and increase the overheads. That's why machine learning is important, to reduce these overheads. So talking about what we are going to consider the outputs of this machine learning that we want you guys to design. I'm going to give you an example where there are 2 vectors per codebook. So there are 2 vectors on the transmitter codebook and 2 vectors at the receiver codebook. And let's say they have an index, 1 and 2. So basically, you're going to have an input for, let's say, some machine learning model, such as deep neural network. And after you feed with these inputs, what's the expected output is to the network or the machine learning model to tell you what is the best pair of beans. For example, in this case, it's the first combined with the second one. And you can basically express that as a pair of numbers, or you can convert on a single index, and then this facilitates sometimes. So basically here, for example, if you choose by the winner taking the largest output of the neural nets, the index number 2, then you know that you have to choose, for example, the red and the green to combine, such that you have the maximum magnitude of the so-called combined channel. And you see what basically it means is that you take the wireless channel age, and then you combine with the combiner vector and with the precoding vector. So the number that has the largest magnitude is going to provide you the largest signal when you pass through this combined channel. So basically, this is the output that you expect the machine learning model to produce. And in a very high level description of the problem number 12, what you see is that we want to select a subset of K beans, but we cannot use the communication system. We cannot impose overhead to the communication system. But the system is not completely blind, because we provide some information about the environment. We provide information from LIDAR, cameras, and also the global navigation satellite system is providing, for example, position, such as a GPS system. And we pose this problem as a top K classification, such that the machine learning can choose, for example, K pairs of indices. So this is the output. And now I'm going to provide you an example of a possible input. If you're not familiar with LIDAR, these sensors, they are placed on top of cars to improve autonomous driving. And then it's basically lights that collects all the obstacles. You see that the kind of information that you have is this kind of point of data, a set of points that basically is describing the objects that it's seeing, basically whenever it reflects. And for our problem, then, we have an urban canyon, a street surrounded by buildings, and you have on this base station a transmitter, and we put receivers on top of the red cars. Typically, we use 10 receivers. And basically, if you look at this conversion, what we have here is from the, let's say, 3D scenario, you have the LIDAR information. And sometimes we process this information to reduce the computational costs, and then we can use this, let's say, features as the input to the convolutional neural net, for example. And to be more explicit, I'm gonna give you an example of this kind of pre-processing. Basically, as you know from machine learning books, if you have raw data, you basically can extract possible features by running a front ends, and then the classifier can work on features that are, let's say, easier to deal with instead of the raw data. And then in our case, the classifier can provide, for example, the bin pairs. Because this is important sometimes in this case, because for example, PCD files that are the outputs of the LIDARs, typically, they may be very large. They are basically X, Y, and Z points. And whenever you try to feed a neural net, you can do that. This is a hint that people can use deep nets that can provide support to point clouds as input, but the computational cost may be huge. So in our case, what we did for the baseline, to give you guys an example, we took the PCD data, the point clouds, and then we convert by quantization. And basically the way it works is like, if you know the position of the base station, you know the base station is right there, you know this area, this zone that you have, for example, the coordinates along the street, you can basically quantize, and it's gonna convert these points, for example, in a 3D array that you have control on the number of elements. So you can control the complexity of the machine learning model by using less or more points on this G array. For example, in some of our experiments, we use 20 by 200 by 10, just because the street goes over the y-axis. So we use 200 points there. And basically what we do is, whenever you find an obstacle, you can put a number 1 in that area. And whenever you have a receiver, you can put -1. Whenever it's the base station, -2, such that a neural net can detect from here what kind of environment the receiver is surrounded. And this is an example of a customized front end that basically quantizes the PCD. And you have more information on this reference that I'm giving here. And an example of a result of that is, for example, if you take, instead of K, I'm calling M. M is the number of subsets. And what you see on this x-axis is that if you increase, for example, selecting 10, 20, and so on, the accuracy goes up as expected. And we did some simulations putting the LiDAR on the car or the LiDAR on the base station. And on this paper, we discussed that. But my point is here is that for this challenge, what we want is to increase this top K or top M accuracy whenever you have the 10 pairs selected. So this is the kind of results that we want you to improve. And in our simulations in this case, we could reduce the overhead to 15%. So instead of looking for all 264, in that case, possible pairs, we used only 10, or in this case, 40 to achieve almost the same accuracy. And we are gonna use this top K just because of simplicity, but there are many other figures of merit for this kind of problems, such as the throughput ratio in this equation. There is this typo here. So basically, now I finished describing to you in a, let's say, big picture, the way that you can work with what we call the baseline. Meaning that if you want to use the features that we already prepared, you can do that. Or you can use what we call the raw, or the, let's say, original data. And basically, if you go to our website, you can download everything that's gonna account for 16 gigabytes, or you can just deal with this baseline data and work only with 512 megabytes. But in this case, you are not designing the front end. You are basically using the features that we provided ourselves. And of course, you may get a better result if you design your front end. And the kind of structure that we have is like, for the baseline, you have the desired output, That's basically the combined channel for each pair of beams. And then you have the positions features. This is something that we use for our baseline. That's basically the position of the receiver. We resampled the images that are taken from 3 cameras along that street. And we also quantized the LIDAR, as I mentioned to you. So if you wish, you can use only the baseline data, but also we provide all the other information that you need if you want to design your customized front end. And I'm gonna talk more about that, but you can see here that you have raw data here, and also you can see some auxiliary files that provide information about the ray tracing simulation and also the process data that you get from LiDAR. It's more complicated if you want to deal with the raw information, but I'm gonna try to convince you that it's useful for you to work with that. But just to talk about the simpler strategy about the baseline codes, we provided some example that you can find on GitHub. And basically we show how to get, for example, the 2 X and Y coordinates, also the LiDAR, and also the images, and then combine using different networks. And then as the output, you can have 256 because we are gonna use 32 vectors on the transmitter codebook and 8 vectors on the receiver codebook. So in total, you have 256 pairs. And you see the codes that you have or you can use to deal with this is basically some regular deep neural net codes for this baseline. So we basically decide how to combine the features. Here we are concatenating them. We are using categorical cross entropy as the loss function, and then we call fit, for example. So if people are interested mostly on the machine learning aspects without dealing with the telecommunication aspects, all those details about LiDAR, etc., then you can basically play with the machine learning using the baseline features. But we really want you to, if you have, of course, time and energy, to understand and play with the raw data. And basically because this Raymobtime methodology is very interesting, as I'm gonna try to describe to you. So what we do basically in these methodologies, we call this guy, which is an open source software that provides the position of cars and people. And then we also get 3D information from the web, such as OpenStreetMap, CADMapper. We combine all this, and then we have 3D scenarios with mobility. And then we run the ray tracing, we run this Blensor, that's a plugin for Blender to get the LiDAR point clouds. Also Blender provides the simulated images, and we can get the positions directly from here. So what we are suggesting, if you work with the raw data, is to come up with feature extraction models, these front ends, such that you provide your own inputs, and then the outputs come from processing the ray tracing data to tell you what's the best beam, right? So I'm gonna try to convince you that it's good to learn about it, because if you look at some of the milestones on communications, you see that when we started with telegraph and radio communication, we had very limited, we assumed limited knowledge about the channel, and most of the designs were worst case designs. But if you look in 1965, we started using channel equalization, using digital filters for, let's say, zero forcing equalization. And then we started doing something called channel probing and adaptation. But basically, we measure and discard. We periodically send pilots, we measure, and then we discard. And what you see now is that we are moving from measuring and discarding to learning from experience. So you are right on time to get more insights on how to use, for example, site-specific systems that can learn and then avoid all these overheads from measure and discard. And if you look at beyond 5G, like 6G and so on, that's expected. Learning from experience is going to play an important role. And I want also to do an analogy with speech recognition. So if you compare the physical layer of mobile communication systems with speech recognition, you can see here the goal is to mimic the human brain. And in the other way, we are designing communication systems, but nature is just giving us the channel because all the other modules are designed by us. spoken language, you are basically provided by the speech. And then it was very important in this case to have data sets by the Linguistic Data Consortium and also DARPA competitions. You can see x-axis is the year, and then this is the word error rate. And these guys got organized such that they could decrease the error, such that nowadays we use speech recognition. And if you compare, it's exactly what ITU is doing now, is providing us data, enormous amount of data, several problems. And it's very nice that we have this possibility of breaking this problem of learning by building and measuring, because, for example, measures on millimeter waves are very expensive. So getting simulated data helps us to cope with this short time that we have to deliver things for 5G and beyond 5G. Another motivation is that we are actually trying, for example, many deep learning techniques, but using very small data. And if you look at this amount of data, as you know, increasing the performance, we are still on this small data region. I'm gonna just show you that I asked the students to look at all papers published in 2019 until August, and look at all that had deep learning in the titles, and then count, they were around 40, the number of hidden layers on the neural nets. And you can see this is the histogram, and this is the number of occurrence. Most of the papers were using only 3 hidden layers. So even if people are calling deep, we are still using very small amounts of data. And that's why it's so important, the ITU challenge that we are talking about now. So now I hope that I convinced you to invest some time on learning Raymobtime, and then I'm gonna quickly describe it and how it fits the challenge. So we basically want to control mobility and also incorporate the time dimension on communication channels. And we have this idea of, you have the 3D scene, and then you keep changing the positions, and then you count each scene as one, let's say, MIMO channel, also LIDAR data, etc. And because these guys are highly correlated, sometimes we impose a long interval just to decorrelate, just to have a very different scenario. And we call a sequence of scenes an episode. So let's say we impose, for example, 30 seconds to wait the cars to move around, and then we get new sets of cars just to have different scenarios from different episodes. And the way it works is we put in a loop the Sumo, that's the mobility software, and also the ray tracing software from Raymobtime, Wireless Insights. And here you see Sumo positioning the cars, and here you see the ray tracing. And basically, doing this technique, we can have channels that have consistency over time, frequency, and also space, such that we can test many MIMO algorithms and so on. I'm gonna just briefly show you that all this is done with a Python orchestrator that invokes the Sumo simulator and also the ray tracing simulator, and all this code is available on GitHub. Also, we want to get realistic data. So what we do, we go to the web, and then we collect this 3D information from different places. Because as I mentioned before, in machine learning, people are gonna deal with site-specific systems. Basically, the system is going to learn about a specific site. It's like in speaker independent and speaker dependent. So basically, you have different ways of comparing things, also of assessing performance. And this is just starting for communications. People usually did communication models and channel models for, let's say, general environments. But with machine learning, we are more interested in learning something that's not going to measure and discard, that's going to learn by experience. So we have different scenarios, and we also get information, as I mentioned, from CAD map to get position of streets, and then we go over a whole process of taking layers out from AutoCAD, because this software requires less accuracy to run fast, and so on. And for the mobility part, we also have information from an OpenStreetMap such that it's very precise, the position of streets. What we get from all these efforts is that if you compare, for example, this is the received power, this is the delay spread, this is the number of vehicles, And these are 4 episodes. So whenever you cross this dashed line, things change a lot. And then you can see, for example, here it was, let's say, night, and here it's like rush time. And you can vary or at least you can observe the variation that you have, for example, on delay spread when you move to different scenarios of mobility. You can impose day, night, and so on. So about Raymobtime, just to conclude, we have around 300,000 channels. They are multimodal. They include LIDAR and so on. They have different frequency bands, for example. You basically simulate the same environment in 2.8 and also 60 gigahertz. And also you have these 10 receivers, and this is something that can be used for many physical layer problems, channel estimation, channel tracking, CSI. The next presentation is going to be about channel estimation using Raymobtime by Professor Nuria Prelchik. And for our challenge, we are going to be using this data set, the number 8. So it is a 60 gigahertz carrier frequency, and you have 20K valid channels. I'm going to talk more now about the problem itself. So as I said to you, there are lots of information about the raw data. And if you look at the ray tracing, basically the way we organize, we call run for each of the scene. For example, run 0, 1, 2, 3. These are different scenes, different scenarios. And if you open one of these folders that we provide to you, you find all these files that basically are the required information to use in this ray tracing software. And if you open this text file here, it's a CSV file, basically gives you information about the cars, the positions, and so on. All this is provided on the zip file. And one thing that's important that confuses people is that we need to tell you if the receiver is valid or not. Because sometimes the receiver is out of the reach of the transmitter, so there is no communication channel, and then we need to indicate that. So you're gonna see this happening a lot. So whenever the receiver is not valid, and for example, you are dealing with these ADF5 files, you are gonna find not a number to indicate that receiver is not valid. So now I'm gonna look at one of that text files in more details. If you look at the first column, you see the episode number, then the scene, then the receiver. Whenever it's -1, it says it's an invalid. For example, this guy is not a valid receiver for some reason. And then maybe you can look at the position and guess why. But we also describe if it's a car, a truck, and also the speeds, the angle, the direction it was pointing, and so on. If you concatenate all this information, this creates another file that we provide. So this is also a CSV file. And if you look at all these, let's say, rows, you can find that we have in the data sets 286 scenes. Potentially, they would have each one 10 receivers, but because some of them are not valid, we have only, instead of 20,000, we have only 11,000 receivers that have valid communication channels. And the way you can see if it's valid or invalid here is just looking at E or I or V. And then we repeat some information that we saw, and also we include this information if it's a line of sight or not. Because for beam selection, if it's line of sight, it's easier, because then the receiver can see the transmitter without any obstacles. And then you are pointing to each other typically. But the non-line of sight, these guys, whenever it's 0, that in this case, they are around 40% of the case, they are harder problems for a machine learning to learn. And this is a complicated way of describing everything, but I hope that the information provided on the GitHub is going to help you to navigate. But let me mention to you that then we have 3 stages. Basically, this first one is whenever we are effectively running the simulation, as I mentioned to you, putting Sumo in loop with the ray tracing software. And we provide this information on what we call auxiliary simulation files. So this is number 1 and 2 here. If you want to open these files, then you're going to see the way we created the data set. And we want to promote that because you can create data sets for your research, and so on, using the source code that we provide. But after we move from this stage to a post-processing, let's say, stage, where we create, for example, here, what we call raw data that has the ray tracing data, also the LIDAR, and so on. So we are at this stage here, and these are the positions on the repository. But then you want to feed a machine learning module, and as I mentioned to you, you may run a front end to extract features. So you have, in this case, all the baseline data is in this situation. And then, as I said before, you can simplify your let's say, task, concentrating only on the machine learning, and then avoiding all the issues with the information in the raw data. But this is gonna, of course, limit you to the features that we extracted ourselves. So basically, to summarize, I really want to invite all of you to participate. We are gonna have this challenge going on until October, but please pay attention on the registration deadline. So we have a very tight deadline, and then we hope to see you guys participating on the global awards in November, December 2020. So we have more details on this website. And now I'd like to thank all the Raymobtime team. We have many students that did a great job. I want to emphasize that most of the code was developed by Pedro Batista and Ailton, but we have many others that can help you along this challenge. And basically that concludes my talk, and I want to finish by inviting you to also participate on the next presentation by Professor Nuria Prelchik. She's an expert on channel estimation and provides very good talks. So I really invite you to participate and learn on how to use Raymobtime to win this channel estimation competition by North Carolina State University. Thank you very much.
Thank you, Adibaro, for the nice presentation. We have learned a lot about beam selection. I hope many people will consider now start working on this problem. Next, we have some questions in the Q&A session window. So I would like to ask my colleague Vishnu to now kick off the Q&A session.
Thanks, Thomas. It has been quite active. Actually, the Q&A and chat has been on fire. So thank you so much, Aldebaro. I think it was this was the first presentation. We had 100 participants. Congratulations! I think, yeah. So there are some very interesting questions, which I think some are fairly basic, which I could answer online, but there are some which we would like to request you. The first one is, could you repeat again what is the input and what is the output from the neural network? So if I understand right, you are using the information from the LIDAR as well as yes, please, yes, the around this slide. Please go ahead, please.
Yeah, I think, thanks Vishnu. I think that you guys can see it this way. Whenever we provide the baseline, we are basically giving an indication on how to use the data. But for example, we know that LIDAR is very effective. So if you guys want, you basically can avoid using other data and then use only LIDAR. Or you can use only the image, for example, only the cameras. But basically, I think the question regards what would be, let's say, the baseline that we provided. In this case, the input is the concatenation of all these tensors. So you can see that you have here 48 by 81 images, and then 20 by 200 by 10, and then the concatenation with two numbers, right? So this is the baseline. But you guys can design any other inputs that you want, combine or fuse information. The only important thing is to keep the dimension of the output.
Thanks, Aldebaro. I think that explains it. Can I ask you to
Sure.
also explain how would I win? So let us say I'm a participant in this challenge. I think there is a lot of interest, looks like, from the participants. So how would I win? How would you judge me if I submit you a solution? How would you determine that I'm a winner, please?
Okay, we are going to provide more information. We have some, but basically we are going to count the accuracy regarding the top 10. So basically you are going to be able to select 10 pairs of beans. And the goal is that the best one is inside the subset. So your network is going to output numbers. We get the largest numbers, the 10 largest numbers, and then we seek if the best one that we found by brute force is inside the subset. If it's inside the subset, then it's not an error. Otherwise, it's an error. And then the way, let's say concretely, we are going to do that is we are going to provide a test set, and then you guys have to label that test set and send us back the labeled test set and also the codes that you use to design everything.
Thanks, Alvaro. I think that makes it very clear. I hope it is clear to the participants how to win this challenge. There were some questions about where the slides are available and whether the participation is open to everybody. So we clarified that it is open to anyone, and people are welcome to join this. There are steps available which we have given in the Q&A as well as in the chat. You can follow those steps to register and select the problem statement. We hope that the interest in this problem statement, you will join Alvaro in finding solutions to this, and you will be able to win. Now, there are some questions about deadlines. I think you already clarified those. Could you go to that slide just in case? Yeah, thank you. I think that is very clear though. There was one question on what was the reason for invalidating some receivers. So I think you told us that they were out of range and there was no valid information from those receivers. Could you please clarify again?
Yes, let me see if I have a figure just to show. Maybe this one. If you see, this is, I don't know if you can see the cars. Basically, you have different color for cars and trucks and so on. This is the area that we are dealing with. It's from Roslin. And the base station is in the middle of this block, right here. And sometimes the receiver is moving, right? And I mean, sometimes it's moving away from the base station. Let's say the receiver is this guy right here. So it may not find enough power to connect such that that receiver is still in the area of interest, but it's also not achievable by the millimeter wave. So in this case, this receiver would be marked as invalid. So whenever we cannot connect to the receiver, we need to mark as invalid. Another situation is that the simulation takes so long that the receiver leaves this, for example, the bus moves to this other position. And so it's not in the area of interest anymore, and also we mark as invalid.
Thanks, Alvaro. There are some questions around, does the LIDAR data come from radars placed on top of cars or mounted on base stations? Could you please answer?
Yeah, that was confusing because I mentioned both. In that paper, one of the reference that I gave, then we had the LiDAR on the base station. For this competition, we are gonna have only on the cars. So basically, this is what confused you, right? So in this paper here, we put at the base station because they are somehow expensive. But you can see the performance is much better if you put the LiDAR on the car. So for this competition problem 12, we are going to use only the LiDAR for cars, and then you get this this is the kind of point clouds that you're going to be seeing. So you can see the car is basically detecting all the buildings around and some of the cars close to it. Whenever there is a line of sight, then there will be no, I believe that you can see that the LiDAR is capable of identifying if it's line of sight or not. And then it helps the machine learning to tell, oh, I cannot point directly to let's say, to the line of sight direction. I have to choose some other direction to achieve the best communication.
Thank you. Next question is, does the CAD file have information of the surface of buildings which are just in front or exposed to the base stations?
You mean, I'm not sure if I understood completely, but you mean all these 3D environments, for example, here you can see one, you have information about dimensions and also electric material. Like, for example, you can say that this guy is concrete or asphalt, the street, or you may put, for example, some woods. You have to provide all this information such that the ray tracing is realistic. And we provide in our data set all this information if you guys want to run the simulations yourselves. So I'm not sure if I completely answered the question, but we do provide all the simulation about the dimensions and also the materials and etc.
Yes, I think that was the question. Yes, I guess that was exactly about the material of the surface. Yes. Next question is, what about data license? Can we share, manipulate, publish, and store on external servers? This is, I guess the question is about after downloading the data, what can you do with it and what is your licensing, please?
Yeah, we have a flexible license regarding our software. You can use it even commercially. And basically, the only data that's not, let's say, something that we provide specific license are the data that we collect directly from the simulations that are with the Raymobtime's wireless insight software. For that, if you want to use, you would have to contact them. But it's okay for you to use for all these, let's say, machine learning experiments that we are planning for this challenge.
Thank you. Where would this model run? In the base station or in the car or both?
The good, very good question. I'm gonna try to give a short answer, but let me get help from this again. When we mention distributed LiDAR here, basically the data is collected on the car, but then it sends sometimes to the base station, and that basically consists on this architecture that we call centralized, right? So basically here you're collecting the information from LiDAR on top of the cars, and then you are sending to the base station that can fuse all the information from different cars and then provide you. We thought that this would give you better performance, but in this paper we couldn't get. I don't know if someone wants to do research on that, maybe they can get better information from that. But on this paper, what we did here was the LiDAR is on the car in this case, and also the decision, the machine learning was running on the car. And then we have a protocol such that would be feasible. For this challenge, the problem 12, we consider that the decision is made on the base station, such that it has the information, it can see the cameras, it can see the LiDAR, and then it's gonna provide the decision. But if you really want to go ahead and think about architecture for autonomous cars in future, then you should read this paper and consider all these possibilities.
Excellent. I think that answers. So basically, you're saying that as far as the challenge is concerned, it is in the base station, but we could also have further work for doing it in the edge or in the car, right?
Exactly.
Next question: the code books are already designed or not?
Excellent question. We use DFT, discrete Fourier transform code books in this case, so they are designed. And basically they are the standard code books for, let's say, 32 vectors and 8 vectors for transmitter and receiver respectively. But this is a good research topic. Like if we are talking about site-specific systems, then of course the system should be learning, for example, using any sorts of supervised learning or reinforcement learning. The system should be learning the best code books, because the base station, for example, would be there, let's say, for a long time. So it could learn by experience. And this is very important topic right now. But for this challenge, they are fixed.
Yes, excellent. I think that is another interesting side of this problem statement. Very interesting. In beam selection, do you have results in terms of BR? Is LIDAR on car a practical solution? Who have to do this process? So I think the second part you already described. Can you touch upon the first part? That is, do you have results in terms of BR?
No, I guess there are papers in the literature, but I'm not aware about specific results. But people are using LiDAR a lot for VR, and I just don't know. Yes, we in our group we never deal with VR, so I don't know. Let's say specific numbers or performance indicators, but probably you find a lot.
Thank you. Why does not your beam selection algorithm depend on channel H as input? Wow, okay. Could you please take that question?
Yeah, the thing is that we are normalizing such that we don't take the input power in account, but you're right. For example, the complete expression for, let's say, a signal to noise ratio, etc., would have to include, besides these factors, also the transmitter power. But if you normalize the transmitter power just to get rid of one term, then you see that this is going to indicate, let's say, how good your choice for the pair of indices. And this is exactly what we want to design, a good machine learning for choosing pair of indices.
Thank you. Learning happens offline or online?
Yes, for this challenge, it's offline, but there are many open issues that you need to learn online, and very good papers just coming showing that, for example, reinforcement learning is feasible for communication systems and etc. So it's a very good research topic to investigate online learning. But for this problem 12, it's offline.
Very good. Yes, I think I have seen some papers on this topic, and but not the combination as you're saying, and also as you described earlier, Aldabaro, the question of running this in the car, that will make it more interesting, and also maybe just to touch upon the practical aspect which we described earlier, it may avoid some overheads of sending these to the base station as well, right? So I think it is quite, it is a greenfield, fertile area. So I think this is the first step, and we look to further research from you on this. My colleague Fatih is asking, can we use further inputs, additional inputs? So things like inputs from other environmental factors or Li-Fi, as input. I guess Fatih means additional inputs for this problem statement. So in addition to the data that you have, is there a possibility of enhancing or enriching the data with other parameters? That's I guess the question.
Yeah, good question. Thank you, Fatih. I think that we basically are allowing people to bring, for example, a complete neural network, like some of the neural nets that you can find on the web, but not incorporating new data, just because it's hard to, let's say, to provide the same opportunity to everybody. So the answer would be no. For this problem, 12, we are gonna require you to be able to design the machine learning using the data that we provide only. So you can get rid of some of the data, not use, for example, the cameras or the positions or the LIDAR, but you have to be restricted to use only the data that we provide. And eventually use a complete neural net that's available on the web for everybody. You can incorporate that already trained neural nets.
Thank you, Aldebaro. I was typing out the response. I think this is also a further very good topic. I think we should once we perhaps the next challenge we should also look at enriched additional data. Another question: GitHub repo has information about installing and configuring software to run. Whether the GitHub repo has all the information or not.
I would say we tried to put enough information to people get started, but we are gonna make an effort to improve it. Because what happens is, as I mentioned, if you concentrate only on the machine learning aspect, dealing with the baseline features, then you need only to install, for example, TensorFlow or PyTorch, all the let's say the deep learning stuff, or you even use, for example, decision trees. You can also find software and just run easily. But if you really want to go over the whole, let's say, pipeline, because it involves several simulators, then you need to be more careful. And let me point that we are going to keep improving this documentation. And of course, all your feedback is very welcome. And just to provide a concrete example, when we are, let's say, debugging the system, when we see errors, it's very nice to position the cars and see what kind of 3D scene is related. So we developed a script that runs with Blender that's called Raymobtime Visualizer. That's also on this GitHub I mentioned, that allows you to see, for example, if you are dealing with example number 30, and then you see an error there, you can visualize all the scene, all the rays, and then get an idea of what was going on. But to give a concrete example, for running that, you have to install Blender. That's a software that requires some steps for installing. So you see that it's not very easy to provide, for example, only a Python install command, but we are gonna keep providing more and more information on the website.
Thank you, Aldebaro. We are running out of time. I'm going to take a chance and slip in one more question from Professor Tamer. He's my great colleague. He's asking, does this data collected from car reveal any location or private information about drivers or passengers' privacy? Yes. So I suppose the answer is no. The last question, Aldebaro.
Yeah, that's a very important question. No, because we are simulating, whenever I mention, for example, the data that we get from web for the mobility part, it was basically the amount of traffic, the speeds, and so on. But all the cars are, let's say, simulated. So there is no information coming effectively from, let's say, a log of some data collection from cars, for example. So all these things is simulated. There is no privacy concern.